Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 38, part A, and we are going to introduce conditional distributions, probability distributions. In our last video series, we discussed continuous bivariate distributions, and we even compared them somewhat to the discrete bivariate distributions. And so we're going to use both of those and cover both discrete and continuous bivariate distributions for the conditional distributions here. And we're going to introduce the PDF and PMF of conditional distribution. And we're going to talk about the properties for both discrete and continuous, something called bias, or I could say specifically statistical bias, and then correlation regression. So let's get started. And we need to define the conditional distribution, or PMF or PDF. So we're first going to let f of x and y be the joint PDF or PMF, whichever one we're talking about, of x and y. And the marginal distributions, of course, are f of x and f of y. And then the conditional PDF or PMF of x given y equals y is this expression, and so I need a capital here. So f of x, this is my random variable, given some fixed value of y, okay? So that is just like the conditional probability of A given B was the probability of A and B over the probability of B. Well, we have the same form here. So we have the probability, PDF or PMF of f of x and y over the PDF or PMF of f of y. Of course, f of y has to be greater than 0. Here, the probability of B had to be greater than 0. Okay. Similarly, I can't say that word for some reason. Similarly, we are going to define f of y given x as f of x and y over f of x. And again, f of x has to be greater than 0. Okay, so let's look at the properties of both discrete and continuous. So the difference here is that for discrete, we're using a summation, and for continuous, we're using integration. So if I remember that the random variable here is the first variable before the given or the bar, and so this is my random variable, and so I sum over that random variables, the values of that random variable, and of course I'm going to get 1, because again, the conditional probability satisfies all the requirements for a probability distribution. And then we have the expected value of x given y, and I see that I made a mistake over here. This is given y, sorry about that. So e of x given y is the sum of x, f of x given y, and again this is e of x given y equals the sum of x times f of x given y dx. And similarly, or same concept, we have e of x squared given y is equal to x squared f of x given y dx integrated over x, or the sum over x of x squared f of x given y for the discrete case. And now for both the discrete and the continuous case, we have these following properties here. And so the variance of x given y is equal to e of x squared given y minus e of x given y quantity squared. So this looks the same as for the variance of x, let's say, e of x squared minus e of x quantity squared. So it's the same form. Now we have some properties that are new. I'm going to start with number 6 here. It's called the law of total probability for expectation. And it says that the expected value of x given y is equal to just the expected value of x. Now, I have put these subscripts in here, unlike your book, because to me, that helped me when I first learned this to keep it straight, all right? And so think about expectation and what it means. Expectation of x equals the integral or sum of x, f of x, dx in this case. And so I'm summing over x if I'm taking the integral, if I'm taking with respect to x here. If I'm taking with respect to y, I have to integrate over dy. So in this first case, we consider x as the random variable and y as fixed, so we would take the expectation with respect to x. But when I integrate over x dx, I get rid of the x's. So the only thing I would have left after I take this expectation here is something in terms of y. And so then the only expectation I could take then would be with respect to y. Okay? So you don't need those if you know how this works. You don't need these subscripts, but it's nice to have them subscripts, especially at first, to help keep this straight. So that's why I've written it this way, to help you out. So if now the law of total probability for variance is that the expected value of the variance of x given y plus the variance of the expected value of x given y is simply equal to the variance of x. You'll notice again that the variable, random variable in the conditional is x, and so that is the variance that we end up with. And we'll prove these. And then looking at number 5, now I want to point out that the variance is always non-negative, so it's greater than or equal to 0. So the variance here inside is going to be greater than or equal to 0. I take the expectation of that. I still have something that's greater than or equal to 0. And regardless of whether this is positive or negative, the variance of it is going to be greater than or equal to 0. So now I get the inequality here from this by looking at the variance of x. And so if it is equal to both this plus this, and this term, the expected value of the variance, can't be negative, then that tells me that this quantity has to be smaller than the variance, and that's exactly what we have there. So let's prove number 6 to begin with. Now, I have switched x and y, so again, you can just redefine x as y and y as x, and you have what I've written before, but this is the way I did the proof, so we'll do it this way, where we're using the expected value of y given x. So x is the fixed value. So when we do this, we should come out with the variance of y, not the variance of x, because that's the variable here. So I take the expected value of y given x, and then I take the expected value with respect to x. So if I consider this the discrete case, I could do it with integration as well, just as easy. But I did the discrete case, and I'll leave the continuous case for you for homework. So if I have y given x, the expectation has to be with respect to y, and so it's y and then h of y given x. That the PDF of the conditional PDF, or PMF in this case. And then I have to sum across, if I'm going to take the expectation with respect to x, it has to be this quantity. So I'm taking the expected value of what's in here. So since it's with respect to x, I take this times f of x, and there's the f of x. And so I'm going to rearrange, actually I'm going to make a substitution using the definition for h of y given x. I'm going to, instead of h, I'm going to use f. So f of xy over f of x, I could use h, sorry if that confuses you, times f of x. And so this and this cancel, and I end up with y times f of xy summed across x and y. Now I'm going to reverse the order of the summation, which I can do. And then I'm moving the y out here with the sum of y. And then I have the sum of f of xy over x, and that's going to give me the conditional or the marginal distribution with respect to y. So I have f of y times y. I sum across y, and I get e of y. So, and that is the proof. Now we can do the same thing with the expected value of the variance of x. So I'm going to take that first term, and I'm going to define it. I'm going to make a substitution for the variance here. E of y squared minus e of y. So, of course, it's conditional. So e of y squared given x minus e of y given x quantity squared. And I've, again, written in the subscripts for you, so you know we're taking the expectation with respect to what. Well, now I can distribute the expectation because it's a linear operator. And so I end up with this expression, and then I have the this expression here. So now I have the expected value of y squared given x. And so by property number 6 that we just proved, that's going to be the expected value of y squared. And then we have this expected value of the square of the expected value. All right. Now we're going to take the other term, and we're going to do the same thing. We're going to say, okay, I have the variance, so that's e of that quantity squared minus e of that quantity squared. All right, so it's just a little more complex. I'll let you look at the details and work it out. And so then we end up with this, and by the property 6 again, we have e of y quantity squared. Okay, and then we take these two quantities here, and we add them together, and notice that I have a negative and a positive, and so these two cancel, and I'm left with e of y squared minus e of y quantity squared, which is the variance of y. Okay, let's look at an example. This is a discrete example. We'll look at some continuous examples as well. So the probability, so I have this conditional, or I have this joint distribution that's given here. So inside is going to be f of x, y. And then we have the marginals. So this will be sub y. And let me clean this up a little bit and say sub x. So we'll be consistent with the notation. We want to find f of x given y is equal to 2. So, and e of x given y is equal to 2, and the variance of x given y is equal to 2. So now I can do, so I see I didn't do, okay, so there it is down below. So before we do that, I'm going to do the probability, well, so in order to do that, I need the probability of x equals 3 given y is equal to 2, x equals 2 given y equals to 2, and x equals 1 given y is equal to 2, because those are the three values of x when y is equal to 2. So here is y is equal to 2, and again I'm going to clean up a little bit here. So here is when y is equal to 2, and so I have the probability that x is equal to 3 given y is equal to 2. That's going to be the probability that x is 3, y is 2, and, you'll see I have the and, over the probability y is 2. So when I looked at the probability that x is 3 here and y is 2, it's 3/10. And then the probability that y is 2 is 6/10. And so I divide them, the tenths cancel, I get 3/6. I'm going to leave it that way. Now I do the same thing for the probability that x is equal to 2, and given that y is equal to 2, so I have the and here, and the probability of y equals 2 is going to stay at 6. So now I have 2 over 6, so that's my answer. Now for x equals 1 and y equals 2, here's the and, 1/10 over the total, 6/10. So I get 1/6 over 1, which is 1/6. Okay, and if I, or 1/6, I'm sorry. And if I add these three up, look at what happens. They add up to 1, as they should. So this is a probability distribution. So now I can write the conditional distribution of x given y equals 2. And that is x given y equals 2. I have x is 1, x is 2, x is 3. And then here are my three probabilities. And of course they add up to 1, as they're supposed to. Okay, so now we can go about finding the expected value of x given y equals 2. So that's going to be the sum of x times f of x given y equals to 2. And so x equals 1 up to x equals 3. I substitute that in and do my calculations, and I get 14/6 or 7/3. Either one is fine. Don't use that until you get to the end, and we're not at the end. So then I can find, so again, I don't want you to use decimal places unless you're asked to, please. So please use fractions. So now I need the expected value of x squared given y equals to 2. And so here's my definition, my formula, x squared f of x given y equals to 2. So here's 1 squared is 1, 2 squared is 4, 3 squared is 9, and I end up with 6. So then the variance of x given y equals to 2 is e of x squared given y equals to 2 minus e of x given y equals to 2 quantity squared, which is 6 minus 7/3 squared, which ends up being 5/9. All right. Whew. So a little tedious, but I wanted to do the discrete example and make sure that you see that it's not just a straightforward, I can figure this out using, I have to make this distribution, this conditional distribution first. I have to do that for y equals to 2. So for each value of y, you have a different distribution, all right? So I hope that helps you understand the concept. All right. Don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, by all means, please come to virtual office hours. That is the best way for me to help you. If you can't do that, email me and send me a picture of your work so I know how you're thinking and how you're approaching the problem, and send me a picture of the problem. And if you send me both of those, I'll be able to help you quickly and get you on your way. So take care of yourself, and we hope to see you next time.